Plus, we have discussed regarding automatic logic synthesis tool and what was the impact of the synthesis tool, because when we do not had any automatic synthesis tool, what was the impact experienced by the designers, and because of the automatic tool, now what is the corresponding advantages of automated logic synthesis tool. Next thing is, now we came to know about the advancement of tools, but how to use this synthesis tool. So for that we should consider which particular HDL description style or constructs the synthesis tool will going to consider. One thing we have to remember that synthesis and simulation are different, which if we are able to simulate a particular program, then it doesn't mean that all the programs that are simulated can be synthesized, but all the programs that can be synthesized are simulated. Okay, whenever we are going to consider synthesis, all the constructs that are defined for the architecture like behavioral or data flow will not be considered. Few of them will be considered and few of them will not be considered. So first, let us consider which particular constructs are considered while generating the synthesis. That is nothing but optimized gate level netlist. So while generating the gate level netlist, mainly we are going to use these are the following construct types. That is nothing but it will going to consider the ports: input port, output port, in out port. Similarly, when a parameters are defined, that is also considered. And when a module is defined with a keyword module, then it will identify that particular construct and the corresponding signals and variables, where we are going to consider wires, registers, and try represents. For example, if we are having tri-state wires and all, in that case we are going to consider tri-state registers and all. So that are considered for synthesis. And similarly, what we are having is instantiation, because when a lower module is instantiated by the higher module, in that case it has to consider that instance. So that is why it will going to consider the construct instantiation. And whenever the tasks and functions are defined, they are also considered. But timing constraint means the delay will not be considered. Whatever the delay we are going to mention, that will be ignored. Except delay, it will going to consider all the other statements. Next, what we are having is the other types of constructs are procedural constructs. That is always statement, case statement, if statement, else statement. All these statements it will going to consider while generating the circuit. Here also we are going to consider case x and case z. These statements are supported, but initial is not supported. Initial is user convenient. If we want some particular variable or signal should be with some initial value, then we are going to write initial in the program. But while making the circuit, it will not going to consider the initial construct, because initial is executed only once, it is not repeatedly executed. And while synthesizing, it will consider all the constructs that will going to execute repeatedly. So that is the reason initial is not supported. And the procedural blocks, like executable statements between begin and end in always statement, and also named blocks, whichever the block we want to enable and whichever the block we want to disable, all these things, this will be considered. But yeah, when we are going to consider data flow architecture, in that case the keyword assign will be considered, but the delay associated with the keyword will be ignored. For example, if I'm going to write assign ash 10 x equals a plus b, in that case ash 10 will be ignored, but it will going to consider the corresponding statement whatever we have written with the keyword assign. And when we consider loop, here these are the loops it will going to consider: for loop, while loop, as well as forever loop. But while executing the loop, it will consider either during positive edge, it will check the repeat the loop, or during the negative edge. It doesn't mean that irrespective of the clock, if it is present inside the always statement, continuously it will execute. It will going to execute, but every during every positive or negative edge of the clock cycle, it will do one iteration of the loop. Like this, we are going to consider the following constructs when we are going to consider Verilog synthesis. Okay, so here I can able to observe that in general, any construct that is used to define a cycle by cycle RTL description is acceptable to the logic synthesis tool. What do you mean by cycle by cycle RTL description? Cycle by cycle means it will be repeating for every cycle. That is known as cycle by cycle description. As I told, in case of data flows architecture, all the statements are concurrent statement. Means as soon as the input changes, immediately that change in the input will be read and it will be processed, and the value will be assigned to particular variable, isn't it? So while doing that, every time it has to read the data of the input variables. So that is why it is considered a cycle by cycle repetition. Okay, but why initial statement is ignored means it is executed only once, it will not be repeated, so it is ignored. So in such case, to initialize our circuit for some particular value, we have to find out some other mechanism, or how to keep the state initial. For example, when we are going to consider counters, so there, until unless if you give the reset button, the counter value will not set to 0. If it doesn't set to 0, it will not going to we may not get the proper count when the counting operation occurs during every positive edge or negative edge of the clock. So in such case, what we have to do means, initially we want to set q equals 0, right? So there what we are going to do means, we'll keep a reset button, and then first it will be initialized from the reset button. So initially the counter will be resetted, and then we start seeing the counting operation. That is how we can make the changes in the circuit instead of considering initial value of q is equal to 0. Okay, and yeah, every vendor will be having his own simulator or synthesis tool. So that is why the capabilities of the individual logic synthesis tool will going to vary. It depends upon which particular synthesis tool we are using. And a cycle by cycle RTL description of the circuit have restriction on ways they construct and are used in the logic synthesis tool. As I told, every logic synthesis tool has its own description regarding which particular construct it has to consider, and for which construct it has to generate what type of circuit. All these things, there are constraints. So while considering a particular synthesis tool, it will going to impose its restriction. That is known as a description of the circuit have restriction on the ways their constructs are used. As I told, till now we have considered only simulation, but while synthesizing, which particular software, synthesize software we are using, that we are not known, isn't it? So as a result, as the technology changes or as the Xilinx software changes, they may change the synthesizing tool, or they may define new constructs which will going to which has been considered in the synthesis tool. So in such case, The circuit design will also change according to the synthesis tool, and each synthesis tool will have its own restrictions or constraints. Using that constraints, the circuit will be generated. And next, what we are having is the another thing, another restriction what we have to consider is the delay will be always ignored, because here the delay is mentioned for designer to analyze. Okay, it is not for a hardware device to tell that it has to consider only 10 milliseconds of delay or 10 nanoseconds of delay. Every component will be having its own delay, that we will not be knowing. Okay, in order, since we do not know which particular synthesis tool we are using and how the circuit will be constructed, just you designer will going to assume this could be the delay. Even though if the technology varies, on an average a particular gate can take this much of delay. Based on that, he used to write delay in the program. And in the simulation, what we will going to do, we will going to check whether that particular amount of delay has been taken or not, and afterwards it will be synthesized. So when once the circuit is synthesized, once again we have to check its functionality manually, and then we should verify whether we are getting the same output what we obtained for simulation. If you are getting the same thing, then the design is okay. Otherwise, we have to redesign. Like this we are going to consider. And also, as I told, initial construct is not supported, so designer must use some reset mechanism to set for any initial value. And while writing any particular program, usually if the corresponding IO port or variable is more than 1 bit, then we have to specify a size. If the value computed on the RHS side is less compared to the width of the variable on LHS side, so in that case what happens, if it will going to append zeros and then it will be stored, isn't it? But when we come for synthesis process, then a precise number of bits should be assigned for every signal or for every wire or register, because it will not come to know how much width data it has to consider, whether it has to consider 8 bit or it has to consider 10 bit. According to that, the circuit connection will going to change, isn't it? So that is why it is recommended that all signal width and variable width must be explicitly specified. And next, what we are having is which particular operators are considered while doing the logic synthesis. Few of the operators are not considered except case equality. That is when all the bits are same, including Z as well as X. That is known as case equality. So that is not considered while performing the synthesis. Only equality and inequality condition will be considered. And next thing, while writing which particular operation has to be done first, so it is preferred to use parenthesis. If we miss the parenthesis, what happens, the operator will going to follow the precedence described in the synthesis, described by the synthesis tool. There we may not get the, sometimes we may not get the required answer. So why we may not get the required answer means it all depends upon the preference or precedence for the operators, means which one should be done first and which one should be done next. For example, if I consider the statement like 5 plus 2 into 10. Okay, so when I mention this particular statement, so what could be the value we have to get? Which one has to be done first, whether multiplication has to be done or addition. So usually when we are going to consider these two different operators, in that case the highest precedence is for multiplication and least precedence is for addition. So as a result, first it will going to perform 2 into 20 and then it will going to add 5, sorry, 2 into 10 and then it will going to add 5. So for that we will be getting the result as 25. Suppose if we do not mention the corresponding uh, restriction, that is which operation has to be done first and which one has to be done next. So in that case, suppose if the precedence, equal precedence is given for addition and multiplication, in that case what happens? First it will going to perform 5 plus 2, that is 7, and then it will multiply with 10. So instead of getting 25 we may get 70 as the answer. Okay, our desired answer is 25 but we are getting 70 because we have not mentioned which one should be done first. So that is the reason first we have to mention the operations which has to be done in a group by the parenthesis, so that we can get the corresponding output which we are expecting. Okay, this is how we are going to consider precedence. And now let us consider the operators. Which operators this synthesis tool will going to support? It will support all the operators like arithmetic operators like multiplication, division, addition, subtraction, modulus, unary addition and unary minus. Here you might have seen that exponent is not there. Okay, and similarly here exponent is nothing but multiplying the same number with the corresponding times, that is 2 to the power of 4 means it will going to multiply 2 into 2 into 2 into 2, like this it will going to perform. So that is why multiplication is performed, not, but not the exponent. And similarly when we consider logical operation, these four logical operations it will going to consider for construct, that is logical and, logical or and logical negation. And similarly with respect to relational operator, less than, greater than, less than, equal to, greater than, equal to. And here you can see in case of equality we are having only equality and inequality, we do not have case equality and case inequality. And when I consider bitwise operator, all the bitwise operators are considered, and, or, XOR, not, XNOR, and all these things. Okay, and similarly when we are going to consider reduction operator, all the reduction operators are considered, reduction and reduction or, like this it will consider all the operation. And here we can consider the shift operation, arithmetic shift, logical shift, both the operations are considered. And when we come across concatenation, we can able to concat more than one scalar or vector. And similarly here we can observe that repetition is not there. Okay, and only concatenation is allowed. And next what we are considering is conditional. These statements, or sorry, these operators are considered while synthesizing the tool, not all the operators. Okay, and some of the examples let us consider. If the assignment statement is like this, assign out equals a and b or c, in that case logic synthesis tool will going to generate circuit like this. So first we have mentioned a and b in the parenthesis, so an and gate will be considered for the inputs a, b, and then or c. So output of the and gate and c will be considered as the input for the or gate. Suppose if A, B, C are of more than one bit, means they are of 2 bits. So in that case, 2 circuits will be considered. One to perform 0th bit addition and the another to perform first bit operation, and the this one to perform 0th bit operation. So like this, it will going to interpret the statement what we have written. According to that, this circuit has been generated by the synthesis tool. Similarly, when we consider the assignment operator with, sorry, assignment statement with arithmetic operator. So here I have mentioned assign sum C out, comma, sum equals A plus B plus C in. According to that, here it will going to consider only one bit full adder. You can see that this is the circuit of one bit full adder. Since all these things are considered as bits, using the one bit full adder circuit it will going to design. when we are going to consider multiple bit addition or subtraction. For example, if I want to do 32-bit addition, in that case, A is of size 32-bit and B is of size 32-bit and C in is only 1 bit. So the size of the A is 32 and size of the B is also 32. So in such case, the sum output should be also of size 32 and carry out as well as carry in should be of type 1 bit. So in such case, what it will going to do, it has to consider optimized circuit. What do you mean by optimized circuit? With minimum number of resource, it should able to get the same output. That is known as optimized circuit. For 1 bit, we are going to consider this circuit. If more number of bits increases, then the same circuit cannot be repeated more number of times. In that case, sometimes some part of the circuit may become redundant and some part will be always active. So it will going to generate some optimized method when the number of bits are more. If the number of bits are less, the same circuit can be considered. In this example, we can see if this is the corresponding simple statement and if it is more than 1 bit, then I told that we are going to get this type of output. But when we are going to consider ABC, instead of 2 bits, if you are going to consider 30 bit or 40 bit, in that case, it will not repeat the same for every 40 bits. What it will do, it has to generate a circuit such that when a 40-bit input is given, then it has to process to get this particular output. That is what we are going to consider. Since it will do automatically the synthesis tool, always we will be getting the optimized circuit. The designer need not necessary to worry about the circuit generation, but after getting an optimized circuit, he should able to follow check whether we are getting proper output or not. And if you are using the conditional statement, it is similar to the multiplexer operation. So how it is similar to the multiplexer operation? It will going to check whether this is true or false. If this is true, it will assign this value for the output. If this is false, it will assign this value for the output. In such case, how the circuit can be interpreted? It is interpreted in this way. Means it will going to consider S as a select line. If S is equal to 0, this S bar will become 1. So as a result, the output mainly depends on I naught. If I naught is 1, output is 1. If I naught is 0, output is 0. Similarly, when S is equal to 1, S bar will be equal to 0. So in that case, always the output of the first AND gate will be 0 and the output of the second AND gate depends on I1. So as a result, we will be getting the corresponding output. This is how it will going to interpret conditional operator as a multiplexer. Suppose if I take if else statement, then also it interprets if else statement like a multiplexer, because if the condition is true, then that particular part of the circuit has to take. Otherwise, it has to go for another part, false condition, isn't it? So this is also translated to multiplexer, and also it depends upon how many number of bits we are considering while considering the synthesis. Here I have taken S as only 1 bit, so it will going to interpret this as 2:1 mux. If you are going to consider S as 2 bits, then it will going to consider it as 4:1 mux. So like this it will going to interpret if statement as a multiplexer depending upon the number of select lines. Okay, this is how we are going to consider. And in general, multiple if else if statements do not synthesize. So multiple if else if statement means See, if there are more number of if else if statement, means if the number of inner loops in the if statement increases, then it cannot be synthesized, it will going to show it as error. If there are only few number of synthesis, means nested if statement, if the large number of nested if statements are there, then it is difficult to synthesize, it will show error. Only small number of nested if statements are used, then we can get a proper circuit which can be interpreted as a multiplexer. Similarly, when I take case statement, so in this case statement also, what happens, depending upon the select line value, the output will be assigned. So that is why case statement is also interpreted as a multiplexer. If statement, conditional statement, case statement, all these things are interpreted as a multiplexer, and using this particular circuit only, it will generate circuit for the entire design. If the number of cases are more, okay, in that case, what happens, the select line value will going to increase. So based on that, it will going to get either 2 is to 4 multiplexer, or sorry, 2 is to 1, or 3 4 is to 1, or 8 is to 1. So like this, it will going to vary depending upon how many number of cases are there. And when we are going to consider for loop, okay, when we are considering the for loop, it is considered as a cascaded combinational logic. Okay, so why we are going to call it as cascaded combinational logic means, see, always in this example we can see, whatever the work we are going to do in one iteration, the same thing will be repeated for all the 8 iterations, isn't it? So as a result, it is considered as cascaded combinational logic, not an individual logic. If it is of only one bit, then it would be an individual logic. Since we are using loop, and this loop will going to run for many iterations that we have mentioned here, according to that, same set of executable statements will be executed. Okay, so that is the reason they are considered as cascaded combinational logic. Each iteration is considered as one set of combinational logic, and the same will be repeated as many times as we want. So it is considered as cascaded combinational logic. And when we are going to consider always statement, it is inferred as combinational logic, sequential and see, when we are going to consider always statement, we are going to consider it as a sequential and combinational logic, because some of the sequential part is mentioned in the always statement using clock signal or synchronization purpose. All these things we are going to consider. Okay, and then whenever for one of the example what we have considered is D flip flop. In this D flip flop, what happens, whenever the clock changes from negative to positive, means from logic low to logic high, we are going to get positive edge of the clock. So whenever the positive edge occurs, always the value of q, sorry, value present in D should be updated to q. Like this it will going to work. And when we are going to consider the level synthesis, so level synthesis means either the clock has to change or the input has to change. In such case, what we are going to do, in both the cases, always statement will going to work, and then when it enters the always statement, we will check whether clock is 1. If the changed value of clock is 1, then Q will be assigned with D. Otherwise, Q will not be assigned with D. Like this, we can able to consider the circuit. And similarly for all, if I write the statement of full adder inside the always statement, this will also do the same thing. Here we are considering the floor bracket, that is concatenation of C out comma sum is equal to A plus B plus C in. So here also what it will going to do, it will treat it as a combinational logic. Similarly, here also it will going to treat this circuit, always circuit as statement as a combinational logic, and repeatedly it will going to execute, because as soon as the input changes it has to execute. So cycle by cycle it will going to keep on executing the statement. And whenever a function statement is called, in that case how the synthesis will going to interpret. Okay, when a function is called, here what we are doing is every function is considered as a combinational block, and whenever it is called, the same functionality it has to do, it will not going to change its operation, isn't it? So it is also treated as a combinational block, and then it will going to generate the circuit required for the combinational block. So here I have written full, the function name is full add, and the inputs for the function are a, b, and the output of the function is, sorry, another input for the function is cin. And what is the corresponding output? It has to add all these bits and it has to return a particular value to a variable full add, and this full add will be a bit of concatenation of carry and sum. Okay, it will going to perform the addition and store data in a variable full add, and wherever it is called it will going to assign that. Okay, that is the reason we are going to consider function as a combination of function as a block of combinational circuit. Okay, though it is called inside the behavioral description, but it will going to perform the operation using the combinational logic only, because when it will not going to take any delay, and whenever you call the function, in that case the same operation has to be repeated. If you are calling the function n number of times, then n number of times also it depends upon what input you are going to give at that moment. Hence, it is treated as a combinational block. And next, what we are having is synthesis design flow. How actually the synthesis design will going to flow, so that it will going to convert RTL description. Whatever the description we have written, it will convert it into gates. In the previous example, we came to know that how it will going to interpret, like how it will interpret function, in the same way it will also going to interpret task. A task is also considered as a combinational block, and there it will not going to consider any delay, and all delays will not be synthesized. While synthesizing, it will only see which particular operations that are defined and what particular constructs that are available. Using that, it will going to generate the circuit, and this is the process that it will going to follow. So first we will going to write the RTL description. Based on the RTL description, it will going to translate. What this translate will going to do? It will going to identify which particular constructs are used, and based on that what particular operation it has to implement using the gate level netlist. And after getting this information, then it will try to identify whether it can be optimized or not. Any function or any particular part of the uh, task, or any particular part of the circuit can be optimized or not. If it can be optimized, then it will optimize, otherwise it will send as it is. Okay, so this is examined in these two blocks. So first it will going to check what are the non-optimized part present in the circuit and what are the optimizable part present in the circuit. So based on that, the optimizable part will be optimized using this block, and the non-optimizing block will be retained as it is. And both will be sent to the technology mapping and optimization. And one more thing, while considering technology mapping and optimization, what we have to do is we have to consider the leaf cells or the technology library defined by the vendor. Which particular leaf cells he is considering and which one he is not considering, means the description for each gate and the description for each logic which he is considering for his manufacturing process. According to that, he has to give the corresponding library, and that using that library it will going to generate an optimized circuit. When while generating the optimized circuit, as I told, it will going to consider the constraints. What constraints? That constraint may be timing constraint, area constraint, like this. There are or operating voltage constraint, all these things. Like this, we will be having different constraints. So based on that and the availability of the uh, gates or technology library defined by the vendor, it will optimize, and then we will going to get optimized gate level representation for the circuit. Okay, for every RTL description, these are the process that will undergo to get the synthesized output of the circuit, sorry, output of the program what we have written. The same thing I have explained here. RTL description describes the design at high level by using RTL constructs, and also it spends time on functional verification, because when once we describe, we will going to check whatever the description we have written is correct or not. So how we will going to check? Using the corresponding simulator we will going to check. Okay, and after check verifying the functionality of the RTL description, then input will be given for the logic synthesis tool. And what this logic synthesis tool will going to do? It will convert the RTL description into the corresponding optimized or intermediate internal representation. So why it is called as intermediate or internal representation? Because it will identify which constructs that are defined, and it will try to identify what type of circuit can be considered to build this particular executable statement. Whether it is a cycle by cycle statement or not, it has to analyze. If it is a cycle by cycle statement, then it has to generate the circuit. Otherwise, it has to ignore. All these things we are going to consider in translation. And then it will going to understand what are the basic primitive gates that are required, and which particular operators are used. According to that, how the circuit optimized circuit can be generated. All these things it will going to consider. And also, as I told, we have to consider design constraints such as area, timing, all these things we have to consider. And then the logic synthesis tool does simple allocation of internal resource. So allocation of internal resource means already the technology library is defined. Using that technology library defined, and then using the corresponding statements that is defined in the RTL library, it will going to check which library cell of or leaf cell can be used to perform the given operation. So based on that, it will generate one optimized circuit that provides the same functionality which we have described in RTL description.